to the first panelists, Jorge Arroyo and Álvaro Pecharroman from Fundación Circe, who will tell us more about the Bamboo project. So I ask the other panelists to keep their cameras and the microphones off. I think that Jorge is going to talk first. Thank you.
Thank you, Selena, for the introduction. So here we are in the, first of all, I would like to say thank you to all the people that already joined to the webinar. This is the second of the series of webinars that we are trying to prove the, or try to learn about the different technology that we already investigating during the Bamboo project. So, can you pass to them? So Bamboo is the acronym for Boosting New Approach for Feasibility and Management by Optimization of Gas and Waste Use. Okay, this project, as Selena said, is financed by the European Commission under the call for the AIDS 2020, and is a part of the SPIRE program. It's an innovation action funding with almost 11 million of euros from the EU. And the duration for the project is 44 months. So we will end the project by February of 2023. Circe performed the role of coordinator, and we have 19 partners that include some research centers and some of the private industries that private companies that work mostly in the demos that we already perform in different sites. So Jorge, if you want to go for a more technical detail.
Okay, good afternoon, everybody. Thank you for connecting today. I am Jorge Arroyo. I'm going to explain the technical part of the Bamboo project. As you know, the energy transition towards a secure, competitive, and decarbonized energy system is a challenge for the intensive industries of the European Union. In this context, Bamboo is developing new technologies which will help to reduce energy costs between 15 to 20%, reducing the greenhouse gas emissions up to 23%, and improving the energy efficiency 17 to 20%. So in this sense, Bamboo project is aimed at demonstrating innovative technologies that can contribute to the European industry decarbonization, including which we are the three main pillars of the project: waste heat recovery, electrical flexibility, and waste stream valorization. We are working on the demonstration of these technologies at an industrial level in the steel, petrochemical, paper, and mineral sectors. In Bamboo, we demonstrate technologies for waste recovery. This is to valorize the energy content of some waste streams due to their temperature and their usage in other parts of the process. The project aims at demonstrating two technologies: high temperature heat pumps and organic ranking cycles. In the case of high temperature heat pumps, they are active heat recovery systems that allow the upgrading of low or medium waste heat to higher temperatures. We are working in a particular application for the case of ArcelorMittal of the steel sector to produce steam which can be used in parts of the process. This application is expected to have a direct impact on the fossil fuel consumption of the plants. In part of the fuel used to generate this steam will be replaced by the energy generated by the heat pump. The second technology contributes to the electricity consumption reduction of the two-plus refinery from the petrochemical sector. In this case, the organic raking cycle technology is studied to recover medium-grade waste heat generated in a crude distillation unit. And with the URC, this energy is converted to electricity, which can be used directly on the plant, reducing the consumption of the grid. The second pillar, which is the electrical flexibility, includes technologies and operational strategies that will make possible that the industries take advantage of lower electricity prices, providing grid services, as well as enable the potential integration of renewable energies. In this context, Bamboo is working in applying the concept of electrical flexibility to the pulp and paper sector, where different strategies and technologies are being implemented to allow the operation of a paper plant as a battery in a regional power grid. The concept in this case means that during summer, where a high share of photovoltaics generation is expected, the plant will reduce or shut down their own generation system to consume more power from the grid. While in winter mode with very low renewable generation, UPM plant generators can be used not only for internal use, but also to supply energy to the local power grid. The third pillar is the waste stream valorizations, that includes technologies and processes that allow the upgrading of different waste streams with a valuable calorific value that are generated inside or outside the plant and can be used as fuels in other processes. Here is the main topic for today's webinar, and Bamboo aims at demonstrating different technologies for the steel and mineral sectors. The concept for the steel sector is to increase the valorization of the off-process gas as fuel to increase the efficiency to the plant and reduce the consumption of fossil fuels. This sense, in Bamboo, we are applying two technologies that contribute to the valorization of this process gas. On the one hand, CFD simulation that allow to analyze the behavior of the combustion when these often low calorific value gases are burned, and a novel flame monitoring system which allow the monitor of the combustion to improve the efficiency and decrease the pollutant emissions. For the mineral sector, the replacement of coke by biomass is demonstrated with a direct impact on the fossil fuel consumption, helping the decarbonization of the sector. Again, we are using CFD simulations to demonstrate how this biomass can contribute to the reduction of fossil fuel consumption and pollutant emissions. And also, we have developed a low NOx burners, which can be increase the share of renewable energy, contributing to the decreasing of the consumption of fossil fuel. This slide gathers the expected impacts of the Bamboo solutions in the potential case that all the solutions were applied together to the 1% of the energy-intensive industries of Europe. As you can see, the reduction in the consumption of electricity per year, the savings which proceed from the substitution of fossil fuels by renewable fuels, the same case that in the CO2 emissions, the reduction are important for all the four sectors, especially for the steel and iron. Finally, I want to remind you that November is the Bamboo Industry Month, when we are developing some webinars to show everybody the technologies developed during the project. Today, the webinar is focused in fuel flexibility in combustion processes. Is the second webinar. I encourage you to register to the rest of webinars. If you can't attend, you have all the information uploaded in the Bamboo Resources webpage and the YouTube channel. So we have yet the last week webinar related to the oversea application in the YouTube channel and in the webpage, the presentation. So thank you again for connecting today. I hope you find of interest the webinar. If you have some doubts about the Bamboo project, you can contact to Alvaro or myself.
Thank you, Jorge. I had a little question. Last time I asked you about the challenges of this project. I wanted to know what you are what you are proudest for about this project.
Especially, we are proud about how the different industries and development centers, research centers are working together to find good solutions. Sometimes it's complicated that because that industries wanted to innovate, and in Bamboo we are getting the industries really involved in decarbonization and in development of the solutions. And this is I think the most proud that to get a full collaboration between every partner to decarbonize the industries.
Great. Thank you again. Now, before getting into the topic of today's webinar, we'll have another round of polls to understand your relationship, you, the audience, your relationship with the technology we are going to talk about today. So first poll, is your company currently interested in alternative fuels? There is a straight no, there are a number of options for the objectives of this interest, let's say. So if it's to reduce emissions, to reduce costs, to promote corporate social responsibility. Okay, so a small percentage, just 4%, is not currently interested in alternative fuels. The highest majority of you are interested in order to reduce emissions. That's very interesting. And there are a few who are more interested in reducing costs and promoting CSR. Second poll. What kind of biomass do you utilize in your company? You might not be using biomass at all, wood biomass, agro biomass, or other waste biomass. So let us know. Okay, most of you don't use biomass, 39%. 30% use wood biomass, and the rest use agro biomass or other waste biomass. Last poll. So this is a bit tricky. According to you, low NOx burners reduce the production of NOx by controlling fuel and air mix, reduce emissions by 100%, present high efficiency at very high temperatures, or are similar to conventional burners but more expensive. What do you think? There is the right answer to this. So most of you selected the first answer, 14% the third one, and then the other ones. I don't know if the panelists want to give the right answer, or do we wait for the panel to reveal it? What do you think? Nikos?
I think the panel gave the right answer. by the 17.5%. The first one, the first answer is the right one. Low NOx burners reduce the production of NOx by controlling fuel and air mix.
Okay, thank you all then. Now we are going to hear about fuel flexibility in combustion processes in energy-intensive industries. I give the floor to Nicolas Margaritis and Roberto Arevalo.
Okay, thank you, Selene, for the introduction and the comments in the poll section. Just a brief, let's say, comment about the poll. Okay, I think that most of the companies here are interested to reduce the CO2, NOx, and other pollutants in their company. This is the a primary scope, but also we can say that this reduction of gases are related very closely to the cost of the production of the company. Biomass is not used for most of the companies here, but there is interest, but also 30% use wood biomass. It's most commonly used biomass, and the less the 30% said that agrobiomass is used, and it's normal because agrobiomass has some difficulties when trying to apply it in the production process. And regarding the low NOx burner, I think the audience chose the right answer. So this is also normal because most of you are technicians here in the today's webinar. So I'm Nikos Margaritis. I'm a research engineer in Center for Research and Technology Hellas in north part of Greece. CEF is one of the biggest research centers in Greece. And especially I'm a mechanical engineer, and I will give a presentation regarding fuel flexibility in combustion processes in energy-intensive industries. A little overview of the contents. We're going to speak about bamboo contribution to climate neutrality. This is a primary scope, and how we can valorize the waste streams of the industries. The challenges regarding the decarbonization in energy-intensive industries. And after that, I will analyze the use case of glacial magnesites, a company in Greece. And Roberto, my colleague, will analyze the use case of ArcelorMittal. Then there is a horizontal section regarding application of flexibility tools, CFD tool, CO2 emissions calculation tool, which is a useful tool for these companies. And the last sections are lesson learned and questions from you. Regarding the first section, as also Alvaro Jorge said,
sorry, Nick, if I can interrupt you just a second, because I forgot to invite the audience to send their questions. They can do it through the chat box at the right side of their screen. So just send them, and we will ask you the questions at the end, or maybe during your panel. Okay, your session. Thank you. Sorry.
Okay, thank you, Selene. No problem. So we're setting here in Bamboo for technologies and processes to allow the upgrading and valorization of waste streams. Usually waste streams has a valuable calorific content, and they can be used as fuels in other processes. So in glacial magnesite, the case study was to replace a part of coke by biomass to do simulations and to try to apply a multi-fuel low NOx burner in the rotary kiln of glacial magnesite. And the second use case was the valorization of processed gas in the steel sector. again, simulations and application of flame monitoring system was the main activities. Regarding energy-intensive industries, what are the challenges? When we say energy-intensive industries, usually we refer to cement industry, lime industry, magnesia, sintered lime, ceramics, glass, steel, and other similar industries of the area. Usually in these industries, we have high temperature process, up to 1,100 up to 1,800 or higher. And of course, we have CO2 emissions that derive either from the combustion of fuels, either for the decomposition of carbonate raw materials, which is an inevitable process, and we can do nothing to avoid them. Also, the use of carbon as a reducing agent. The fuel combustion, as known, entails high thermal losses and may also lead to other pollutants like SOx, NOx, CO, and other pollutants. We're talking usually for continuous production cycles that require steady energy supply. This is very important, and is also a challenge for these industries. And energy efficiency and productivity can be increased by thermal insulation, energy recovery to use the heaters, heat pumps, organic drying cycle, or automation and digitization also in the companies can contribute to energy efficiency and productivity. And also use of variable renewable sources, good energy management system, and DSS tool. All these things can help increasing the energy efficiency of energy-intensive industries. Regarding the decarbonization, the top priority of EU member states is to gradually go to a low carbon economy, which means 80% reduction in emissions by 2050 compared to 1990 levels. CO2 emissions, in case of magnesia industry, derive from fossil solid fuels, which are related to their production process. This type of emissions must be tackled so that these industries will not face issues due to continuous increase of CO2 prices. They have some CO2 free allowances until 2030, according to the regulation EU 2019. But after 2030, they're going to face increased CO2 prices, and so the problem of cost reduction will be always important. So here we can see that the CO2 price was in 2020, in March 2020, below 40 euros per ton. And we see that gradually it increases. It reaches in January, February 2022, it reaches almost 90 euros per ton, and now it's in 4th of November, it was below 80 euros per ton. So this is a challenge, how to mitigate this CO2 emission cost, and the answer, a partial answer of this question will be to replace some solid fuels with biomass. Biomass is carbon neutral, so CO2 emissions can be reduced. One of the drivers for biomass and coal co-firing is the increased environmental performance at a modest cost. And what we earn when we replace the biomass, biomass with percentage during co-firing, we earn a reduction of SOx emissions. Also, biomass helps to reduce mainly NOx emissions. And biomass can also reduce flame temperatures, and the reduction of flame temperatures also leads to lower levels of thermal NOx, and also a reduction can be the case if high moisture biomass is used. Regarding the use case of glacier magnesites in the bamboo project, we had to support the Greek demo, which is located in Chalkidiki, north part of Greece. Here we see the calcination plan in Gerakini mine, the installation, the premises of the company. Here you can see the rotary kilns of the company. What they produce natural magnesia here from magnesite. Regarding the production flow sheet, first of all, they do mining, extraction of raw material. Then there is a stadium of pre-beneficiation, separation of magnesite from the waste rock. Then there is the beneficiation, the qualitative separation of magnesite grains. Then we have the calcination in the rotary kilns that I showed you before. What means calcinations? Magnesite is transferred to magnesium. The product for GM, the final product, is magnesia. And magnesia can be calcined magnesia that is produced in the range the temperatures between 900 and 1100 temperatures of the kiln. Or another product is the deadbed magnesia, called DBM. We have the CCM, the calcined magnesia, and the deadbed magnesia, the DBM product, which is more challenging in its production because it's produced in temperatures well below the 2000 Celsius. So, what are the GM's degradation magnesite targets and challenges? GM has had some targets, and this was the reason also to participate in Bamboo project. Main target was to increase the energy efficiency of the calcination department and globally at the Gerakini plant. To reduce mainly the dependence on fossil fuel, they use their main fuel is coke, pet coke, and so they want to gradually replace coke with biomass in order to reduce CO2 emissions and NOx emissions, to allow flexible energy consumption according to market prices, and also to take some and check some good practices regarding waste heat recovery in their process. For example, ORC or heat pumps application, or any other technology that have been studied in Bamboo project. What are the challenges for GM? The main limitation resides in the high temperature required to produce DBM. As I said before, DBM is a challenging product to produce because you need very, very high temperatures. And these temperatures can be accomplished without conventional fuel, let's say pet coke, in the fuel mix. You need a high fuel specific consumption. You have high fuel specific consumption. So another challenge, if you replace coke by biomass, is to have this big amount of biomass to secure a stable feedback to the factory. In the right, but against in the same time, you have to produce also to preserve the product's quality. So you can't miss something, or you can't do any activity that can harm the final product quality. And another challenge is that high temperatures can cause damage risks to the kiln lining and other processes to the factory. What's biomass? The biodegradable fraction of products, waste, and residues from agriculture, forestry, and related industries, as well as the biodegradable fraction of industrial and municipal waste. Here, GM, in the framework of our project, wanted to utilize wood chips and sunflower husk, so wood biomass and agro biomass, in order to replace some pet coke. The choice, the kind of biomass, was restricted by availability of this biomass in the near area of demo site, because also other biomass would be the case to do the experimental campaign. For example, olive kernels, but in the specific time season, no quantities of this biomass was available in the market. So GM has to adapt and choose the current time the sunflower husk as main fuel to substitute the pet coke. Here we can see the heating value of biomass related to pet coke. So pet coke is the main fuel of GM. It has almost 8,000 kilocalories per kilos, its heating value. And the other biomass fuels, olive kernel, sunflower husk, sawdust, wood chips, have almost half the heating value of the pet coke. So what this means that you have to double the quantity of biomass in order to produce the power, the energy for the process of GM. During the bamboo project, a new low NOx burner was modified and adapted in the current in the rotary kiln 3 of Gerakini mine. A full-size burner, around 20 megawatt thermal, was designed and constructed and was assembled and installed in rotary kiln 3 of Gerakini site calcination of Grecian magnesite. The burner head is 4 and is inserted into the rotary kiln for a significant part of its length. Here in 1 number, you can see the preheated primary air. It splits into outer and inner air. 2, this is the outer air, and this is the inner air. Liquid fuels are fed through 5 with this pipe. Also, we have the possibility to adjust the swirl, the air swirl, to adjust the pressure, the air pressure regulation, the inner-outer air ratio through levers and that we can see here. And this burner is the old burner head that was replaced by this. So this was the Greek demo, the application of this low NOx burner, in order to check its efficiency in reduction of NOx emissions during the production of magnesia products. Here again some details regarding the design and construction of the new low NOx burner applied in rotary kiln 3 of Gerakini mine. Here you can see is from here comes the liquid fuel, and from here this cycle comes the solid fuel, and swirl. We have inner air swirl and outer air swirl, and swirl is can be achieved through these adaptations. For example, here we have max swirl application, and here that these pipes are not swirl, let's say, but here we have no swirl. So when we have to increase the swirl, a dedicated lever in the burner switch this solenoid, let's say, pipes, and swirl L is achieved. So the initial burner test was successful, and first trials were very.
We have a question. We have a first question.
Yes.
Not sure. What is the CO2 reduction in fuel gas combustion biomass instead of coke?
The CO2 reduction. Yes, the CO2 reduction, we will see it in the final slides. It depends if we in this case we replaced 50%. We had an energy substitution of biomass by 50%, and the CO2 reduction was 25%, because there is a CO2 amount that can be avoided due to the calcination of magnesite to magnesia. So there is a standard CO2 that's always there, and the CO2 that we can reduce, it's only in the fuel combustion. but I have a slide in the end for the specific CO2 reduction in this case. Okay, here in this table, we can see how NOx, the NOx, the percentage that they reduced. We see that with the old burner, the NO2 were 1,670 milligram, and they were reduced with the new burner by 44%. This is a big reduction. Only with the application of low NOx burner without biomass. The entrance of biomass will lower more the NOx emissions produced. Here you can see some pictures of the demo, both for the Gerakni mine, the plant. Here we can see the feed port of magnesite. In B, here the petcoke chip, and here is the biomass feed port along with petcoke feedback. Here is the petcoke in the yard of the Gerakni factory, and here is the biomass that is used in order to replace 50% of petcoke by energy during the process.
Okay, another question, can coke still be used in the new burner in case of no available biomass?
Yes, of course. You can use it. You can use LNB with 100% petcoke. These results refer to 100% petcoke. There's no problem. But these burners are designed with this way to also to can handle also biomass except for petcoke. But petcoke is the easy way. Here you can see the fuel mix preparation. So here we have the biomass, sunflower husk pellets, the twin rotor in order to succeed the granularity of the biomass. And in another silo, we have the petcoke. And petcoke and biomass are entered in this feeding, in this silo. Where the mixed fuel is prepared, petcoke and biomass. Then we have a mixer here, a weighting system, and the mixed fuel. This is the image of the mixed fuel, petcoke and biomass. You can see that, okay, the color of petcoke is more intense. So this fuel goes here in the low NOx burner that we said before. In the entrance of the rotary kiln 3. During the experimental campaign, we had the flue gas emissions monitoring in order to check the CO2 emissions and NOx emissions, and also this from this card you can see you control the fuel mix, biomass and petcoke anytime in the rotary kiln. So here we can see the SO2 and NO2. This table summarizes the main results of the experimental campaigns that were conducted in February 2022 at GM with the support of us, of Research Institute. And these concern various DBM grades and petcoke substitution rates 50%. This was the maximum substitution rate that was achieved during these experimental campaigns. And you can see also the comparison with 3 cases. The first case was only petcoke. This is the business as usual case. Only petcoke in the rotary kiln. You have this SO2, this NO2, and around 1,500 Celsius. When we used sunflower husk pellets with petcoke, you can see that we have petcoke 1,000 kilos per hour, the flow rate, And we have also sunflower husk in the fuel mixture. We have a 50% contribution of petcoke energetic with biomass, almost the same temperature. And here we can see that with the introduction of biomass, we have again extra reduction of SO2 and NOx and NO2 emissions. This is about 20% extra NO2 reduction. In total, with this biomass substitution, you have 6% reduction in NOx. Seth has in Ptolemaida in Greece, we have a laboratory dedicated to chemical characterization of solid fuels. We have all the necessary equipment to analyze according to ISO 17020 biomass fuels, solid fuels, SRF, municipal waste, and any other solid fuel that can be used in a production in the combustion can be physical, chemically characterized by us here in Ptolemaida in our lab. So here we see the main results that petcoke analysis, sunflower husk analysis, and mixed fuel analysis in terms of moisture, ash, volatiles, chlorine, hydrogen, nitrogen, sulfur, chlorine in the fuel, and also energy content of the fuel. So we see here the high energy content of the petcoke, around 8,000, and half of this, around 5,000, is the heating value of sunflower. So the mixed fuel that's going that we receive, or with the mixture of these fuels, has a high heating value of around 6,700 kilocalories per gram energy content. So the main conclusions of co-firing in GM kiln: the operation of the new low NOx burner was quite efficient and effective in reducing NOx emissions up to 40% without biomass. An experimental campaign focusing on pulverized biomass mixed with petcoke for co-firing mode was conducted. The biomass of choice was ground sunflower husk pellets, and this was chosen based on heating value, cost, and availability criteria. A special feeding dosing system was necessary in order to handle the new fuel and not to have blockages in the production process. And with this new special feeding dosing system, a 50% substitution of petcoke was realistic. And this substitution reduced NOx also extra 20%. So 40% without biomass and another 20% reduction with biomass. So in total, 60% reduction of NOx emissions and almost 50% decrease of SO2 emissions. SO2 emissions are reduced because, as you can see here, biomass usually has very low sulfur content, 0.12, in contrast to petcoke that has high sulfur content, almost 3.12%. So the final fuel has around 2% in the mixture, so is smaller than 3. So smaller than sulfur concentration in the final fuel means that you have reduced CO2 emissions in your gas, in your flue gas in the end. The planning of GM is to maximize co-firing ratio to above 50%, taking into account the existing technical limitations and without compromising product quality, as I said in the beginning. GM has 3 rotary kilns. This was applied in the rotary kiln 3. So this can be replicated also to another 2 rotary kilns of GM. But important is that the extensive use of biomass means that you have to invest in relevant infrastructure dedicated biomass mills, biomass petcoke mixing slows, in order to handle better the biomass petcoke mixture. And so an investment has to go there in order to handle the new fuel that you are going to use in your production process. Now I give the floor to Roberto in order to analyze the use case of ArcelorMittal, and I will also tell some things in the end for the flexibility tools.
Before giving the floor to Roberto, I have another question. What is the humidity of biomass and how can it affect the heat consumption, since the water can absorb heat from the combustion?
The biomass has usually high moisture, 4%. This means that you have to use more biomass in order to achieve the right energy you want to produce your DBN or CCM product. And the high moisture is good because you reduce the flame temperature, and when you reduce the flame temperature, you reduce the NOx emissions. So it's not bad to have this moisture in the biomass.
Okay, so I think that Roberto we can give the floor to Roberto. Roberto, can you hear me?
Yes. Yes. I'm going to share my screen. Okay. So thank you all for coming. My name is Roberto Arevalo from Circe Technology Center, and I'm going to present the use case of ArcelorMittal regarding fuel substitution or alternate fuels. Well, ArcelorMittal hardly needs a presentation, worldwide steel producer. We've been working with a factory in the north of Spain. And here the focus is in using process gas as a fuel to substitute part of the natural gas that they use. The process gas that we are interested in is BFG, blast furnace gas, that is produced in one of the early processes of the plant. Well, this is an schematic of the blast furnace gas. And here, well, the BFG is just a subproduct. Usually it could be regarded as a waste. It is currently used in plant to already to make some substitution of natural gas, also to produce steam, and it is also sold to other companies that can use it to produce steam or to other uses. One of the advantages of BFG is that it is very highly available in the plant. Here you can see a comparison of the natural gas with the BFG. And as you can see, there are many differences. BFG has a composition very different. Of course, this is just, let's say, a typical composition, because BFG can have varying compositions depending on the details of the process. But you can see that the actual content of methane and other carbon compounds is very low. And also very important, the low heating value is very low compared to natural gas, is more or less 1/10. This means that when we are using BFG to replace part of the natural gas, we have to use much higher flows. And although BFG is highly available in the plant and many of the piping is already in place, we have to be careful because these high flows can put stresses and other problems to the piping. The activities that we have done in Arcelor together with Arcelor is a twofold study. We have carried out an experimental study in a gas laboratory facility, which is a small chamber with a burner. And here on the left, you can see, maybe you can see some pipes that simulate the load of the burner. In the right part of the screen, you can see the part of the computational model that we have used to perform simulations of this facility and to perform the simulation of the combustion of mixes of natural gas. In the previous slide, I show you the actual mixture of gases that we have used, 70% BFG, 30% natural gas. This is in volume, and you can see the final composition of the gas. This is the matrix of the cases studied. You can see, well, there are no figures in the graphics due to confidentiality issues, but you can make a comparison between the cases, which are 9. There are 3 cases of natural gas changing several conditions, another 3 cases of BFG, 100% BFG, and 3 cases of a mixture of BFG and natural gas, which is the previous mixture, 70%. So one thing that you can see in the first graphic is that the flow of fuel varies greatly. As I said, the low heating value of BFG is very low compared to natural gas, and this is what explains the differences that we can see here in the first graphic. Then we have the temperature of the fuel. You can see that when we use only BFG, we have to heat it up a bit to improve its fuel capabilities. Also, the share of air is changing. Okay, when we use BFG or mixes of natural gas. And well, then we have the more inputs, the secondary airflow. The temperature of the air is more or less the same in all the cases, a bit higher for BFG, but more or less the same. And here in the middle, you can see flow of oxygen. This is a lens here. No, it's not. Sorry, it's not the detail of the burner, but the burner can introduce in the furnace a stream of oxygen just to supplement the combustion. We use it only with natural gas. And in the right part, you can see the power generated. That is actually a bit higher with the mixes that we have used of BFG. And in the lower part, you can see the equivalence ratio and the fuel primary air ratio. As I said, this is a twofold study. So we have made all these experiments actually in the gas lab facility in the furnace. And we have also carried out the simulations of all these cases. And the aim is to, first of course, to learn what we can from these mixes, with whether it is possible or not to substitute natural gas with BFG, and how much natural gas we can substitute, but we also want to study whether it is possible to actually use CFD simulation to predict the behavior of the combustion. Because of course it is much more easier to do a simulation than to carry out an actual experiment in the facility. It is much cheaper also, and you can try many scenarios. So
there is a question, does the BFG need any treatment to be used as fuel?
No. It is, as far as I know, it is used without pretreatment. Yes, it is used as such. Okay, so these are the results of the simulations and the actual experiments. So here you see the red bars are the measurements in the gas lab facility, blue bars the simulated experiments. And we have measured a few, I am presenting here just a few of the measurements that we have done. Again, we cannot show the actual figures, but you can compare the cases, which is the interesting thing after all. And here, for example, for the exhaust gas temperature, what you can see is that when you introduce BFG in the mix of fuel, you reduce the temperature of the exhaust gas. This is to be compared with this other plot in which you can see the heat transfer to the load, which I remember is a flow of water that is close to the floor of the furnace, and you can see exactly the same trend. So when we are introducing BFG into the mix of fuel, we are reducing the heat transfer to the load. Okay, so up to some point, this could be expected because we know that the BFG has lower heating value. Of course, one can change the. We have only used one share of one mix, one blend. It is to be expected that one can change this result by changing the mix of fuels. And here is the outlet oxygen. That is one of the outputs that is usually monitored to check how the combustion is performing in the furnace. And well, here you can see that the figures are actually not so different between the different mixes of gases. And here we have finally we have also measured the NOx emissions. And you can see that there is, by one side, there is a clear trend that when we increase the BFG in the mix of fuel, NOx are reduced. One possible immediate explanation for this is that the temperature is also a bit lower, as we can see in the first plot. So when we reduce the maximum temperatures, we also always reduce NOx production. But well, this is also an interesting point of using BFG, because if you match the right composition that you need to transfer all the heat that you need to your load, you can still be reducing the amount of NOx. Here, as you can see, there is a big change between using only natural gas or using BFG or a mix of BFG. Secondly, regarding the comparison between the simulated experiments, the simulated results and the measured results, the actual experiments, we can see that actually the results come very close. For example, in the first plot, we can see that all the blue and red bars are very close to each other, meaning that the simulations give results that are very close to the actually measured in the gas lab facility, in the furnace. And the same is for the heat transfer load and for the oxygen outlet. Well, here in the oxygen, there are there are some differences in some cases that deserve further study, but also very interesting in the NOx production, let's say. The comparison between simulated and measured results are in general very good. There is only one case in which there is a mismatch, but in all the other cases we come up with essentially the right results. So from these results, from this transparency, we can learn that, well, what is the behavior of the furnace and of the load when we change the mix of fuels, and also we can learn what the simulations can give us. And for me, one important result in this complete study, beyond the fact that we can use actually a process gas to substitute for natural gas, is that we don't need to carry out the experiment in an actual facility always, that we can have a validated computational model and use it many times to carry out many experiments, changing many variables, and having very reasonable trust in that the results are going to be essentially correct. More important even than the actual figures when dealing with simulation, especially in a process so complicated as combustion, is that the trends are the correct ones. So for me, it's not really at all important, for example, that the oxygen is exactly the right value, but that the trend that we obtain with the simulation and the trend that we observe in reality are the same. So you can always come up with valuable knowledge from carrying out a simulation. Okay. So my part is more short. I come right now to the conclusions. Well, in general, comparing the experiments and simulations carried out with BFG, meaning only BFG as fuel and the mix of BFG and natural gas, we can see that, of course, when we use only BFG, we need much higher flow of gas because of the low heating value. Okay, this is pertaining to the question. BFG had to be preheated by 10 degrees Celsius. So, okay, it's not a huge pretreatment, just a small one. Regarding thermal load, so heat transfer to the load, okay, with BFG only 50% of the thermal load was achieved, but using a mix we reach 80%, and for the rest 20% can be tuned, of course. This could be done, for example, with simulation to come up with the right value of the mix that would give us the 100% load. The temperature of the gas in the chamber with BFG was 200 to 300 degrees lower. This is to be expected also. Instead, when we use a mix, the temperature of the gas in the chamber is just only very slightly below the required. NOx emissions are significantly reduced in both cases. Of course, with BFG, they are more reduced because the temperatures are lower. But the main point is that when we use a mix of BFG and natural gas, they are also reduced. But beyond the point of reducing NOx emissions, I think that nowadays, the pressure to reduce natural gas consumption is very pressing, even more than when we started the project. So I would say that in general, the results of this study are very encouraging, very interesting. And again, as I was saying, also from the point of view of the use of computational tools to carry out this kind of studies, and afterwards the required modifications in the actual process. Okay, now is the part of application of flexibility tools. Okay, this slide is from Nikos.
Yes, just to okay.
You can go ahead. If you need me to pass the presentation, you tell me.
Okay, I will read from you. Okay, we had we used the tools developed by Circe and Seth and Cosmotech, developed in the framework of Bamboo, a web application allowing users to easily simulate and keep track of alternative scenarios. It adapts its CO2 calculation tool and CFD tool in order to, with this way for companies to take, let's say, quick results by simulating alternative scenarios, either for the replacement of biomass in the food waste and to exact, let's say, quick results. This platform is available in the site. Okay, it needs authorization access, and then it can be extended with automated optimization and sensitivity analysis algorithms, and connected to Azure Digital Twin for real-time data updates if needed. Here you can see a screen of this web application. Okay, Alberto, please change the slide. Okay, here it's yours.
Yes, thank you. Okay, so well, this is the as Nikos just said, this tool has like two parts. One for related to CO2 calculations, and another one related to a digital twin of the rotary kiln used in GM, one of them. Here in Circe, we have carried out simulations of this rotary kiln to produce a digital twin that is going to be used in this tool to predict the behavior of the combustion inside the kiln when we change the mix of fuel, when we are using a mix of coke and a certain type of biomass. So the way to produce this digital twin is to first produce a CFD simulation of the rotary kiln. Here you can see just a few features of the simulation. You can see the geometrical model that we have set up for the rotary kiln, and you have the physics that we introduce in this simulation. We simulate the combustion of the coke or the biomass. We simulate also the gaseous chemical reactions. We take into account mixing by turbulence, heat transfer by radiation and convection. And the model predictions are, well, in a simulation of this kind, a physical simulation, you can really have all the fields that you need: the temperatures, velocities, turbulence, gas composition, pressures, etc. So for this project, we chose just a few of them, which were the temperatures and velocities along the kiln, and also the gas composition and the temperatures at the exit of the kiln. Okay, this is an example of the results of CFD simulations. In the left, you can see a plot along a cut along the rotary kiln. You can see the base case, that is the case using pet coke and the old burner with only one source of swirl, and the other cases are using two sources of swirl. And in the right part of your screen, you can see simulations comparing the base case using only coke and several substitutions of biomass. You can see numbers 30, 40, 50, that stands for 30% energy substitution, 40% energy, 50% energy. Energy is supplied by the biomass. And here we're tested two types of biomass. Okay, so we made a campaign of simulations, many simulations, simulating many scenarios. And after we have all those data, we produce a digital twin that is a mathematical representation, much simpler than the whole simulation. And what the digital twin allows to do is to obtain results in real time, okay? Because it is using the results of all the previous simulations. And this is a snapshot of the same tool, but this would be the part of the CFD or the digital twin application. Here you can see two plots of the, I suppose they are temperature or velocity. Here in the right part, you I extracted two plots just to see them better, of the temperature along the kiln for several scenarios, and the velocity of the kiln also along for several scenarios.
Okay, this slide, it's also an answer to an audience question regarding CO2 emissions reduction from pet coke substitution with biomass. So we had developed a calculation tool in order to calculate how much is the reduction in CO2 emissions according to the biomass substitution, and also what means this in production cost due to CO2 prices. So the amount of CO2 is reduced to 61,000 tons when 70% substitution rate is achieved with biomass. As you can see here in the table, we have do some simulation with 0, 30, 70, 50, and 70% substitution of biomass. As you can see, as I said early in my presentation, we can do nothing until now for the CO2 that are emitted due to decomposition of magnesite to magnesia. This is something we can do something to avoid. So that's why you see that we have a stable number for CO2 emissions regarding decomposition. What we achieve through co-firing is that we reduce some CO2 emissions due to solid fuel combustion. So if we are here now in 50% reduction substitution, we achieve this is a reduction of CO2 emissions. Or if we apply, if we increase the substitution rate, then the CO2 emissions reduction is also increased. So that's why I said before that the reduction in total CO2 emissions is about 50 to 25% when in the scenario that we checked, that we examined in a GM. Because we have this number that can be changed. And also the next slide, this calculation tool show us some, as I said, okay, we use biomass to reduce CO2 emissions, NOx, NOx, and CO2. but this reduction of CO2 is translated to production cost avoidance. So if you achieve to reduce CO2 emissions, then also you earn some money in the production cost. So the production cost drops around to 11 millions, over 10% reduction, when we substitute 50% petcoke with biomass. This was the case for GM. 10% reduction in production cost is a very big amount for such kind of companies and with their huge balances. And this graph was made when the production cost, this graph shows us the production cost when we use sunflower husk pellet or olive kernel or wood sawdust. You can see here that we have this production cost, but this production cost reduces to 9 millions when you use olive kernel. But this was not the case for the GM because they didn't find olive kernels in such a quantity at that time of experimental campaign. So this tool helps you to understand, according to the current prices of CO2 and the fuel prices that always changing during the year. So if you have this, if you have this tool, the company has this tool, can predict according to the fuels prices what the production cost means in terms of according to substitution of biomass. So it says that, okay, I will substitute this percent, I will earn this one. It's a good tool for predicting the production cost and CO2 emissions for such kind of companies. And in the next slide, okay, now we have two slides, one lessons learned from GM and one from ArcelorMittal. So the first step regarding waste streams valorization is to measure which are these waste streams. Regarding biomass use, it's important to check the availability within the area in order to reduce the cost of value chain. It is not worth to buy biomass 1,000 kilometers away from your plant. This is not cost efficient. So biomass use will be efficient for the company if it has some biomass in a perimeter of 50 kilometers, let's say 100 kilometers around the plant factory, because the value chain and the cost value chain are very important in these activities. Regarding the low NOx burner, it is able to adjust in different temperatures of the kiln, depending on the time of the product. It's working quite well in GM. Of course, co-fired biomass has the challenge that you have to invest and do a special feeding dosing system in order to handle the new fuel mixture in your equipment. And the production cost is something important. It has to do with CO2 allowances. So you can control the share of biomass in your production process in order to, according to the CO2 price and according to the fuel price of your main fuel, in order to earn some budget for your company for energy savings. Okay, Roberto, you can present the next slide for ArcelorMittal.
Yes, as a summary or lessons learned from ArcelorMittal, well, we learned that we can use BFG to reduce energy consumption, and in the way to reduce NOx emissions. Of course, we have to tune the blend of fuel that we are going to use. We need to characterize properly the gas because, as I said at the beginning, the composition and for example, the low heating value and other properties of the gas can depend on how it is produced exactly. the use of enriched oxygen in natural gas combustion has been tested, and it has been observed that reduces the NOx emissions. This was only used with natural gas. So the reductions that we have seen in the results with BFG and the mix of BFG and natural gas are without the aid of this enriched oxygen process. Okay. Well, yes, due to the properties of the BFG, it may need some conditioning, but is very low. As we have seen, the 100% BFG was heated up 10 degrees, so it's not really a difficult conditioning. And very interesting, the CFD has been proved to be accurate when predicting the results of the combustion in essentially all the measurements that we have seen. And it has been seen to be accurate also predicting the trends when we change, for example, the mix of fuel or some other conditions. So it is a valuable tool to carry out modifications in our processes. And this is it. Thank you very much for your attention. And if there is any other question.
So this webinar is almost finished. We have a couple of minutes. If you want to ask questions, you can write them in the chat box. There are a few I can ask them now. Can other processed gases be used to reduce natural gas consumption in steel factories?
Yes. We haven't tested it in this particular project, but in other projects, you can search for Vulcano, for example, Vulcano project, in which Circe also participated, and there we tried other processed gas like COG and other ones in different mixes. But I have to say that at least for that project, the conclusion was that BFG was the best for substitution for natural gas, but other mixes are possible.
Okay, one last question. Is it necessary to modify the burner to use BFG as fuel?
No, the burner that we've been using in the actual experiments was the same that was used before. As I said at the beginning of the part of Arcelor, you may need to be careful with the piping in the factory that goes from the BFG from the furnace to the burner, because you are going to need a huge amount of gas, so you need a lot of flow very fast, and sometimes this can put some stress in the piping, but the burner itself is the same.
Okay, so it's all the time we have for today. Our webinar ends here. I hope you enjoyed it, and I thank all the participants and panelists for being with us. I remind you that the next webinar of the series will take place next Wednesday, November 16, at the same time, 3 p.m. Central European Time. And we will talk about combustion monitoring in the steel industry using computer vision and machine learning. I hope to see you there. So have a great afternoon and see you soon. Bye.
Thank you. Bye.
Thanks a lot. Bye.